The development lifecycle of software engineering is generally described by the V model as shown on the screen. The number of various outputs are developed at each phase of development in this lifecycle. Of these, some of the outputs may exist independently, but most of the outputs are closely related. In other words, the output created at a specific phase of development is used as input for the next phase, resulting in the deliverables of that stage. For example, you can create system or product-level system requirements documents based on top-level requirements, such as marketing requirements documents collected by the product planning team. These system requirements documents should reflect all of the requirements gathered by marketing. In addition, it is further created with adding internal and external corporate standards, constraints, and external environmental conditions to develop the product. Thus, the child document must satisfy all the requirements mentioned in the parent document. And a lot of rework from software development efforts are common in the testing phase, which is the later part of the development process. One of the main causes is known to be due to an error in the requirements. For example, misunderstanding of requirements, requirements missing during development phases, errors that do not reflect changes in requirements. IAG Consulting says more than 40% of the total development budget is wasted by wrong requirements. So how can we avoid these errors? It is in software requirements analysis and specification activities. We analyze software requirements and make specifications when developing software. Analyzing and specifying software requirements in this way has three effects. First, it increases the efficiency of communication among developers. As you can see on the screen, two developers are discussing the system. However, when one verbally explains the complex software structure, they are not able to communicate with each other. But if you have a blueprint that shows the same thing at a glance, it's much easier to understand. It also improves development efficiency because the communication between developers is much smoother. The larger the project, the more communication between developers. So even if you only spend less time in communication, you can spend more time on development. To this end, Unified Modeling Language was born. In other words, modeling makes it easier to understand and communicate with the system when a lot of developers are developing at the same time. Second, the requirements analysis and specification can solve the problems in the systematic ways. In other words, there is a systematic mechanism to reduce defects and costs from software. Look at the graph on the screen. The limitations of code-based development can be seen as the software becomes more complex and result in losing systematicity. Therefore, the proportion of defect is significantly increased. The bigger problem, however, is that these defects are likely to be found later in the development. In other words, defects actually occurred at the beginning of development, but it is not found there. It is often found at later phases of development. The later you discover a defect, increase exponentially in the cost of fixing and maintaining it. Therefore, if you develop more systematically and find defects in the early phase, you will not be delayed in correcting the defects in the later phase of the development process, and you will also be able to save costs. In other words, it is possible to drive more efficient development. Let's look at the third part. The greatest effect you can get from software requirements analysis and specification is the source code reuse. The drawback of code-based development is that code reuse is difficult. For smaller developments where the software was not complicated, you may not have felt the need for code reuse. It would not have been a big inconvenience to develop new software for each new product. Even if you reuse it, you would have to go ahead and apply the old codes all at once and debug it for the new product. However, as with recent trends, consider the case in which a product is connected to multiple products and merged together. That results in complex software. Code reuse is indispensable to meet the time to market. In case of model-based development using UML, it provides a mechanism in which various kinds of application can be developed together with the idea providers and implementation specialists. As a result, you can create higher quality applications and make code reuse easier. As such, there is some limitation to develop smart devices with just code-based development technique. Modeling is the way to go beyond these limits. As you can see on the screen, the global trend has already been moving into model base from the code base. In other words, we are advancing to MDD, model-driven development, and MDT, model-driven testing. In the past, assembly language has become in common, and as software has become more complicated, the use of assembly language, which is very common to the machine language, has become more and more limited. Thus, the languages such as C, C++, and Java have emerged and become popular. But as the software has become so complicated that languages such as C, C++, and Java are facing the challenges and limitation again, the modeling language has emerged as a way to overcome this. Structured analysis is the most used in system analysis and embedded system analysis. The analysis phase aims to analyze the requirements and then construct a specification for the logical function. Because the purpose of the analysis is to define what of the system to be developed, it focuses on identifying the information flow between functions and functions that construct the system rather than the specific details of the functions to be implemented. To do this, a data flow diagram that emphasizes the flow of information and deliberately ignores the control sequence is applied. By not expressing the control sequence in this way, it is possible to express information flow between functions and function more concisely. Also, there is a state machine specification, a notation that is useful in the analysis phase. Due to the nature of the embedded system, the system must be able to respond appropriately to external events that cannot control their order. If a developer has an unexpected situation and events, this leads to a defect. The state machine specification explicitly shows cases and events that might be in the future. As a result, it provides techniques for expressing the analysis and decisions on various combinations without missing. The screen briefly described the structured analysis process. When companies in the field analyze requirements, they have been doing with these three steps. If there is a problem with the user, the customer, or the field, the first thing is to create a system context diagram to understand the overall system behavior and context. Second, do a stepwise decomposition. Repeat for all processes to break down the process across multiple levels. The third is to create a P-spec for each process and run the requirements analysis and specification tasks by describing in detail what inputs, outputs, and contents each process has. Now, this is the structured analysis method. Here we will look at the development of the automobile cruise control system, which is widely used as an example of embedded system. This system provides the ability to maintain the specified speed by performing its operation instead of driver's Excel operation, when appointing a specific speed for the driver's convenience. The screen is a brief description of requirements related to the ACC system. After reading this requirements statements, please review the development process on the following screen. The figure on the screen is the system context diagram for automobile cruise control example based on the given requirements and system configuration. This system context diagram illustrates the extent to which the automobile cruise control system interacts with the car. According to the system context diagram, the automobile cruise control system to be developed has functions to control the throttle mechanism by accepting input from driver shaft sensor, engine sensor, 4-position lever, brake sensor, and digital clock. These external elements are represented by a rectangle that represents input-output in DFD notation. And the automobile cruise control to be developed is represented by a circle that represents a process in the DFD notation. The arrow between the process and the input-output indicates the flow of information. Information is described in dotted lines for events that reflect the importance of the point of occurrence. In addition, data that does not reflect the importance of the point of occurrence is represented by a solid line. Now, let's create a data flow diagram. The data flow diagram of the automobile cruise control system that was first decomposed based on the system context diagram is shown in the figure. As shown in the figure, the functions of the automobile cruise control are divided into distance and speed measurement, which calculate large axles of car, and automobile control, which controls the entire automobile cruise control. This first decomposition identifies the key function of the system and is usually split into 7 to 10 major functions. Please note that this example is not common because the nature of the example has only 2 decomposed processes. Once you have created a data flow diagram, you will need to develop a data dictionary. The data dictionary defines the details of the data shown in the data flow diagram. The items described in the data dictionary are things that are meaningful for future design, such as the range of values. The screen is part of a data dictionary created during the actual development of the automobile cruise control system. Please click the mouse button to see the contents. This time we will look at the requirements analysis by object-oriented development methodology. The example is System Development of Deposit Service to Support the Business. A bank is trying to develop a system to support the deposit service for customers. Assuming the system to be developed should support deposit-related convenience services for customers who visit the bank directly, customers who use ATMs, and customers who use the Internet. Requirements may be described as per the screen. Here the design scope is set and the actors and the ultimate user goals are identified. The primary actors are ATM customers, Internet banking customers, and bank clerks, and each goal depends on the role of the primary actor. For example, the goal of deposits is the goal of customers visiting the bank with the money to deposit in their accounts, but it is not the goal of Internet banking customers. In addition, the secondary actors are extracted according to the goal of the primary actor. In the case of goal account transfer, the secondary actor other bank system has been extracted because it includes the account transfer to another bank. And the design scope sets the system boundary. For example, the design scope of a system that supports depositor services to ATM customers will be a deposit service system that includes multiple ATMs. We will continue to map the goals defined in the example requirements to the use cases one-to-one and express the relationship between the actors and use cases in the use case diagram. The figure on the screen is the use case diagram of the UML. In the figure, we use different notation to distinguish the primary actor from the secondary actor. In UML, an actor can be represented as a class because it is an object with behavior. In the case of external systems, that is secondary actors, they can also be expressed in UML classes. Of course, you can mark it as a bar-shaped person. The first step is to refine the use case diagram. In initial use case diagram of the diagram, some use cases may have common behaviors to the inside. These common behaviors can be separated into sub-use cases. The table on the screen shows the process of extracting common behaviors from the use cases shown in the initial use case diagram. For example, use case balance inquiry and transaction history inquiry for Internet banking users commonly require an account inquiry. In addition, balance inquiry, transaction history inquiry, and account transfer use cases can have login/logout for Internet security access in common. The results of these tables and the initial use case diagrams can be represented as refined use case diagrams as shown in figure. Based on the results of the previous table, the relationship between primary use cases and sub-use cases is represented as includes in the refined use case diagram. This time, to see the dynamic behavior analysis, let's develop a sequence diagram for the use case of deposit. This example only introduces two object lifecycle classes for convenience. The table shows how to assign responsibilities related to objects participating in an account opening scenario. There are two events. There are several participating objects, which define the responsibilities that each event and participating object must perform. Message passing between objects follows the criteria described in the table on the screen. O indicates an acceptable message sequence. The diagram on the screen is a sequence diagram developed by applying the responsibility assignment result and message exchange principal table. As there is an actor called a bank clerk, it is a sequence diagram in which the participating objects are listed on the x-axis, and which events occur between each object and what behaviors are being performed by which responsibility. This time, we will learn how to write a requirements specification based on an example written in accordance with the industry standard IEEE. The screen is part of Bank A's software requirements specification, which contains the result of analyzing functional requirements and specifying process breakdowns. Functional requirements include all the details that a software developer needs to design, which describes how the input is transformed into output. Because it is the most important item in the specification, all the requirements must be clear and verifiable. Each function can be decomposed into several subfunctions. In addition, when describing the functional aspects of the development target system in the specification, you should select the appropriate diagram based on the application methodology. For example, when developing using a structured technique, create a data flow diagram. In the object-oriented methodology, create a use case diagram, and in the information engineering methodology, create process decomposition diagram. An example of the screen describes a process decomposition diagram by information engineering methodology. The next screen is the definition and specification of the base process or use case of the process decomposition diagram we saw earlier. I/O data systems for each function identified with a function definition for each process are identified. And for input, it can be identified and defined in the standardized forms that your business uses. In this input-output specification process, external interface data not belonging to the development scope is also defined and identified.